Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I'm learning quickly, I don't claim any real expertise. Today, we're looking at the 72nd Project Euler problem. As always, I will link to both the problem and my repo in the description. Let's dive in. Problem 72 is counting fractions. Consider the fraction n over d, where n and d are positive integers. If n less than d, and the highest common factor between n and d is equal to 1, it is called a reduced proper fraction. If we list the set of reduced proper fractions for d less than or equal to 8, in ascending order of size, we get all of those. It can be seen that there are 21 elements in this set. How many elements would be contained in the set of reduced proper fractions for d less than or equal to 1 million? Okay, so if you've seen problem 71, this is going to be extremely familiar. Problem 71 asked us to get the fraction immediately to the left of 3/7 for this same set of reduced proper fractions for d less than or equal to 1 million. But now we want to know how many reduced proper fractions are there. So let's go ahead and open up our code here. Caps lock. Okay. Once again, we'll just grab our daytime, and in this case, we want our limit as well. So what we did for the last one was pretty specific. So we're not going to be able to do quite exactly the same thing. But we are still going to want to do, I think, for d in range, and then for n in range. So I'm going to steal this bit. This is actually going to be 1. Okay, obviously I don't actually want to do that, I'm just keeping that. And then I'm just going to make a fractions dictionary. And here's why. Because if you make a dictionary, all of the keys have to be unique. So what I am going to do is I am going to say fractions dot set default n over d zero. So all this is doing is it's looping through and it's going, okay, if this is n over d, then we are just going to go through and we're going to set that key. So then all we would need to do is print found length fractions dot keys elements in set. Actually, I'm going to start doing this. Okay, so the problem with this is... I don't like that. Never mind. I take it back. Problem with this is... although that code took less than 5 minutes to write, it's going to take more than 5 minutes to run. And I know this because I worked through problem 71, where I had to get clever about reducing the problem set in order to have it run efficiently. Okay, so reduced proper fractions, there's got to be a better way to limit this. And actually, come to think of it, this builds on another earlier problem where it's just going to be the sum of all relative, okay, going back. Problems 69 and 70 had to do with this function phi of n, where the result is phi is the number of relative primes to n. So in here, instead of calculating like this, what we really want to do is we want to calculate the phi of every d and add it together. So, problem 70, we actually were calculating phi in a particular way where it was just phi minus the prime factors of phi. Or, sorry, n minus the prime factors of n, which in this case, d would be our n, which is not confusing at all, I'm realizing. Okay, so sum is actually going to be 0. Let's go back to problem 70 or 69, so we have this chart, at least for numbers less than 10. Okay, so I'm not sure of a clever way of calculating phi for every number. But for prime numbers, phi is just n minus 1. So 2, phi is 1, 3, phi is 2, 5, phi is 4, 7, phi is 6. So something that we can do, going back to here, we can find all of our prime numbers, and that should at least give us a place to start working from. So for d in range, phi equals... it's always going to at least be 1. If is prime d, then phi is equal to d minus 1. Else let's see. So otherwise, we have to actually calculate phi. Let's ignore that else for right now. And just do sum plus equal to phi. Obviously, this is not going to be the correct answer, but let's see now. Okay, so every number is either a prime or primes multiplied by primes. So all we have to do is find the prime factors and subtract them. So let's see, the number 8 has 3 prime factors, all of them are 2. And if we do 8 minus 2 minus 2 minus 2, that's basically 8 minus 6, which would be 2. But then we have to add back 2. So it's the number of primes minus 1 is the number we have to add back. Because, like, for 9, 9 is 3 times 3. 9 minus 3 minus 3 is 3. Ooh, but then we'd have to add back 3. So then maybe that does not quite work. Does not quite work. Okay. All right. So if a number is 2 primes multiplied together, 2 unique primes multiplied together, then its phi is itself minus both of those primes plus 1. But if it is not unique, so for instance, this 9 is 3 times 3, and it's basically phi happens to be 9 minus 3. 8, it's 2 times 2 times 2. So 8 minus 2 minus 2. Kind of seems like let's see. Eight minus 2 is 6. But since we're dealing with factors, it's more relevant to think about 8 divided by 2? Ooh. See, this gets complex relatively quickly. Another way of looking at it would be like the phi of 2 is 1, and 8 is 2 to the cube. So 1 times 3, and then add in another 1. That gets to 4. So for 9, you'd have to add 2, though, because it'd be 2 plus 2. Okay, so for the smaller numbers, I'm not quite certain. Or for the numbers where... Let's see. Let's see, my formula for problem 70 was phi equals n minus its 2 prime factors plus 1. So if it were phi, could also be calculated as, let's see, phi of n1 would be n1 minus 1, and the phi of n2 would be n2 minus 1. So let's grab this and think through some maths. And let's see if we can... Let's just make this x, y, and z for the sake of algebra. And let's say we want to set it equal to x minus y minus 1 minus z minus 1. And then it would be like, what does that plus 1 equal? So... I think it would be plus 3, yes? So if we did x minus the phi of y minus the phi of z, then added 3. So what this is leading me to is we need to do, for the addition, let's see, if we did the phi of the factor, then we need to add 1 and the number of factors. So let's think this through for 8. So 8 has the factors 2, 2, and 2. So the phi of all of those is 1. So it would be 8 minus 3. Well, that just leads to 8 minus 3 plus 4. So that doesn't quite work. At least I think this would be equivalent. Maybe not. Let's see. So this is the correct answer. Yeah, it would have to be, because if you subtract 1 twice... Okay. I still think it has something to do with calculating how many relative primes there are, has something to do with calculating the prime factors. It's just that when they are not unique, it becomes confusing. So... So the logic of, like, this formula was... Let's go back to problem 70. Logic of this formula was, like, n is equivalent to n1 times n2. n1 and n2, both primes. So there are precisely n1 factor multiples of n2 that are below n1. n, and there are precisely n2 multiples of n1 that are below n. So or wait. Let's see. Because, for instance, let's get to... Let's do, like, 2 times 11. So 2 times 11 is 22. So 22 is 2 times 11. So phi of 22 is equal to 22 minus 2 minus 11 plus 1. That is meant to be a 2 there. So 22, how many even numbers are less than 22? It would be 2, 4, 6, 8. Right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it would be 10 multiples of 2. And then there's just the one multiple of 11. So phi of 22 would equal effectively 21 minus, let's see, 21 minus 11, because 10 plus 1. So, let's see, the relative primes of 22 would be 1, 3, 5, 7, 9, not 11, 13, 15, 17, 19, and 21. Which is kind of the number. It's not quite the number of primes that are less than 22, but it's close. So if we take 21 minus 11, we get 10. So if my guess is correct, this should be like 10 numbers. Which it is. So it's not... it's not really this. It's more 21 minus 1 minus 10. Which equals 10. So it's subtracting phi. So let's see if this works for 9. So if the same thing worked for 9, phi of 9 would be 8 minus 2 minus 2, which would be 4. But that does not work because it's 3. The actual phi of 9 is 6. So in this case, it's simply 8 minus 2 because it's a square. Phi of 3 being 2. Yeah, phi of 3 is 2. So, by that same logic, phi of 8 is equal to 7 minus... Let's see, it's 2 times 2 times 2. There are 3 multiples of 2 that are less than 8, which we know because there's 3, so it's the number of 2's. Okay, so for numbers where it's the same prime repeated, it's the number of those, perhaps? Let's see, so that would mean that the phi of 25 would be 24 minus 2 because it's 5 squared. But I don't think that's correct. let's see, the 525 would be 1, 2, 3. Ooh, maybe it is. Not 10. It would be 11, 12. Not 15. Not 20. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 525 should equal to 20, not. Ah. So 9. Okay. So 5n when n equals prime x times prime y is n minus 1 minus x minus 1 minus y minus 1. So it's really I'm if I'm remembering how to do algebra correctly, all of these minus 1s can be added up into 1 minus 3. Um, so but that's not what I used back in problem 70. I had to add 1, not subtract 3. Okay. So if I did 22 minus 2 minus 11, then I would have 22 minus 11 is 11, minus 2 is 9. I'm not sure where we're getting plus 1 instead of minus 3. Ah, because we have to distribute. So x minus y minus 1 is the same as x minus y plus 1. So n minus 1 minus x minus 1 minus y minus 1 is actually equal to n minus x minus y minus 1 plus 1 plus 1. Because, let me break that into one more step here so it's easier for everyone else to see. So n minus 1 minus x plus 1 minus y plus 1, which equals n minus x minus y minus 1 plus 1 plus 1. And these two cancel each other out, so we just get this. Okay. So then phi of n when n equals prime x times prime x is more like n minus prime x minus 1. Which should just be n minus prime x. So for 25, that means it would be 25 minus 5, which is 20, which is in fact what we see because it's all the numbers below 25 except for 5, 10, 15, and 20. Just 4 numbers. So 20. Double checking that it works for 9. 9 minus 3 is equal to 6. Good, good. Now, for 8, the correct answer is 7 minus 3. And there it has to do with the fact that it's 8 minus every multiple of it. It's 7 minus the 3 multiples of 2 that are below 8. 2, 4, 6. So generalizing again, phi of n when... Come on, computer. Okay, my keyboard is acting super, super slow. Phi of n when n equals prime x cubed is n minus 1 minus 3. That can't possibly be quite correct in every case. So let's look at 27. According to my guess here, it would just be 23. So 27 minus 4 equals 23. But I think that there are more factors of 3 that are less than 27. Let's just list the factors of 3. We know those are the ones that we have to get rid of. So 1, 2, 3, 4, 5, 6, 7, 8. So the actual correct answer is 19. It's 27 minus 8. So I think we can generalize these two cases. 27 minus okay. So, let's see if we can generalize this even further. So phi of n equals n minus 1 minus n divided by f1 minus 1 minus n divided by f2 minus 1, etc., where f1, f2 are unique factors of n. Let's work with this and see if it gives us not is prime. I'm actually going to steal something from... Well, nope, I deleted that. I wrote this in the last video and ended up deleting it because I didn't use it. But I for I in range length is prime if is prime I... Actually, I had previously checked whether it was equal to true, but this returns a boolean. Okay, so what I've done here is I've basically grabbed a list of primes. So for I'm going to set this limit down to 10 just so I can see if it um, is giving me the answer I expect. So for p in primes, I'm going to have a number, or I'm going to say if d mod p equals 0, actually, I'm just saying num equals, I'm going to say x equals d. F mod p is 0, then I want to say num is equal to x divided by p minus 1. I'm going to convert that to an integer. Actually, no, never mind. I was thinking maybe I only calculate that. Oops. Before, and then, because what I need to do is I need to set x equal to, um, I need to set x equal to this right here. And my computer is seeming to struggle to keep up with what I'm doing, which is very interesting. And then phi is going to be minus equal num. And I want to do while mod p equals 0, x equals mod divided by p. So, like, for the case of 9, or for the case of 8, it'll go through this loop 3 times. Steps back down to 10. Okay, just for the record, the correct answer for 10 is going to be 1 plus 2 plus 3, or 1 plus 2 plus 2, which is 5, plus 9, 4 is 9, 11, 17, 21, 27. We're expecting an answer of 31. And I have a feeling this is not the most efficient way of doing things, but let's see how well it works. Definitely going to be more efficient than the thing that's been running for almost an hour. That's why it's still... my computer's fighting me, is because I left my program running. Whoops. Okay, I've used my task manager to close that because it was getting unruly. Okay, so 33 elements in set. I said that we were looking for 31. Go back to problem 72 is what we're working on. Okay, so my hypothesis was that if we do this for a limit of 10, we should find 33 elements. Let's do it for a limit of 8 and see if we're close to the actual answer of 21. Okay, so we have an off by 1 error somewhere. Found by of I or B. I'm gonna change that back to 10 so we can compare with problem 69. Why not just have both up? I don't know. Okay, so it should be 1, 2, 2, 4, 2, 6, 4, 6, 4. 1, 2, 2, 4. 6 is incorrect. It should be 2. But we're getting a 3. Are the other ones right? 6, 4, 6, 4. No, 10 is also incorrect. So 6 and 10 are wrong. Six is... they're both 1 higher than they should be. let's see, prime, prime, not prime, but got the correct answer. Prime, not prime, wrong answer. Prime, not prime, but correct answer. Not prime, but correct answer. Okay. So it seems like we aren't working quite right for this case of multiples of two different primes. I don't think this is the problem, but let's see if it gives us a different answer. Okay, no. But this will save us when we get higher numbers. Okay. So for 6 and for 10, we are not properly subtracting one of the numbers. Six for the equals 10. And okay, so here we're setting phi to 3 twice. And here we're setting phi to 5 twice. when in reality, let's look at 6. So 6, we should be doing... Let's see, so 2, 6 divided by 2 is 3. There are 2 multiples of 2 less than 6. Ah, I see why. This has to be D. Let's see if that gives us the correct answer. 4 for 10. Okay, so we set phi to 5 for let's look at number 2 or number 6 first. So we're setting phi to 3 because if phi is 6 minus 1, which is 5, and 5 minus 2, which is how many multiples of 2 there are under less than 6, is 3. And then there is one multiple of 3 that is less than 6, so we set phi to 2. Okay. So, deleting that, deleting this, deleting this, setting our limit to 8, just to double check that we get 21. Correct answer. Set our limit to 1 million. This is probably going to take some time to go through, but let's see how long it takes. I have a feeling it'll take over our 1 minute time limit, but let's find out. Okay, so obviously it's taking a bit to run. I believe it's already been over a minute, so this is clearly not our most efficient solution. I wonder how long it will take to get to the correct answer. This is probably not going to be an efficient enough algorithm here. I had, for a previous problem, started going and looking at the unique factors of a number. Um, and that would be another way of doing this, but... Okay. So, that might be the correct answer, but it took over 4 minutes to find, so... we have to make our algorithm a bit more efficient. And... I'm not 100% sure exactly how I'm going to end up doing that. So... I'm gonna make a factors dictionary. Is this going to be more efficient? I'm not sure. It'll delete this for loop and this while loop, incidentally. Well, it won't delete the for loop, it'll just make it different. I'm going to make this less efficient. And the reason that I'm going to do that is so that for every k, I can say what prime factors it has. So... I think it's append. Okay, so then I'm gonna bump this back down to 10. so we have 4, 6, 8, 9. Those are the non-prime numbers less than or equal to 10, so this makes sense. I don't need this anymore. Instead, I am going to say for f in factors of d, d divided by f plus 1. And we don't need to do that. Let's see if that gives us the correct answer for 10. Nope. We're off by 1 somewhere. Bringing back our printing of factors. Two for 4, 3 for 6, which is incorrect. Yep, then 2 for 6, that's correct. 4 for 8, which is the correct answer. 6 for 9, 5 for 10. Should be setting 10 twice. Five isn't showing up as a factor of 10. We say if I equals 5, print adding k factors. Ah, that's another slowdown, isn't it? Okay. So now it's going to take a lot longer to get through setting the primes, but this should be practically instant. 4 for 10 is correct. Okay. Now, Set our limit to 1,000,000. See how long it takes. Now, okay, stop that. We don't want that print statement in there. Okay, so that ran in a total of about 3 seconds. And it came up with this 273, 878, etc. And unfortunately, we can't go back and look to see whether that matches our previous answer that I was more confident in. But let's see if it's the correct answer. It is not. Okay. And I know why. I'm going to have this just go all the way up to limit plus 1. This is a little bit silly because it's excessive for finding primes, but it is not excessive for finding factors. So it is going to take a bit longer. Okay, still about 3 seconds, but it also came out with the same answer that we know is incorrect. So, never mind. So, I think that I've just gone down, like, the totally wrong path here, maybe? Formula, finding, let's see, totient function. Okay. Okay, this formula basically says that the value of phi of n is equal to n multiplied by product of 1 minus 1 divided by p for all prime factors of p of n. For example, phi of 6 equals 6 times 1 minus 1 half times 1 minus 1 third, which is equal to 2. So 6 times 1 minus 1 half is 1 half. So that's basically 6 divided by 2, which is 3. 3 times 1 minus 1 over third, which is 2 thirds. So 3 times 2 thirds is 2. Okay, can I see the Python tab? No? Okay. Okay, the first one is the simple solution of iterating through all numbers from 1 to n minus 1 and count numbers with greatest common denominator within as 1. Okay. So, okay, so this is kind of just exactly where I was going previously. Where it's describing these different ways of getting different cases. But let's go ahead. This is more or less what we are trying to do now. Where it's consider every number p where p varies from 2 to 5n. If p divides n, then subtract all multiples of p from 1 to n. Update n by repeatedly dividing it by p. If the reduced n is more than 1, then remove all multiples of n from result. So I can't see the other languages, unfortunately. I don't know exactly why, but the website appears to not work. But that's basically what we are doing. Um, so I think perhaps there's something else going on where maybe the way that I am going about getting how many elements are in this set is wrong. So, but that doesn't make sense to me. Let's go back to that other article. So, in other words, for 6, 6 divided by 2, then times 2, then divided by 3. So 3 times 2 is 6, divided by 3 is 2. Looks silly for 6, but Let's see. This is sort of where I'm going with this, but maybe it's not quite correct. So in this case, we want to set phi equal to d, and then m for multiply. No, that doesn't really work. So top is equal to f minus 1. Bottom is equal to f. So phi. So num equals phi times top. And then num equals phi divided by bottom. And then phi equals num. Go back to the number 8 just to make sure we get 21 still. No. Something's wrong. Oh, right. I was so used to doing 10 that now I'm confused because I did 8. Okay, so missing quite a lot. Multiplying 4 by 1/2. Multiplying 6 by 1/2. Multiplying 3 by 2/3 for 6. Ah. There we go. Okay, so that's a different number, which makes me feel better. And that is the correct answer. So I wasn't incorrect about my approach. I wasn't incorrect about my general approach of find the phi's, but I was incorrect about my specific approach of how to find phi, or how to find the result of that quotient thing. Okay, so got the correct answer. The program runs in just over 2 seconds, really. Either way, way over under a minute. So let's see, reviewing what we did here. We saw this problem of how many elements would be in this set of proper reduced proper fractions. We recognized that, oh, all of the reduced proper fractions, all of the numerators would be, or the set of all numerators for a reduced proper fraction for a particular denominator would be the same set as the relative primes for that number. And then we went ahead and tried to calculate relative primes, and we had a lot of false starts here, but I'd say we're looking good now, and I'm going to call it there for today. And as a reminder, if you would like my help with whatever code challenge you are facing, please check out the link in my description. I'll catch you in the next one.